Alright everyone, welcome to our first set of guided notes for Trig, Math 1316. We are going to be getting in some basic trig definitions in this first set of notes. Let me go ahead and kind of rearrange some paper so maybe those words showing through won't be a distraction. Okay, so again, hopefully a lot of this will be review. We're going to talk about some terminology to do with geometry that you will need to know to be successful moving forward. A line is just an infinite set of points that moves in two directions. A line is determined by any 2 points on the line. So a line is determined by 2 points on the line. If I make this my line, and it looks like I'm running out of purple already. If I make this my line, I can call this line AB, or I could call it line BA. Because it doesn't matter which direction I'm moving, it's going to go on and on forever in both ways. So I don't have an end point. These are just 2 random points that are on the line. Now a line segment is a portion of a line. And a line segment has 2 endpoints. So if I just want to talk about this part of the line from A to B, that is line segment AB, notice the difference in the notation. I could also call it BA because both of those vertices are endpoints. And then we have a ray. A ray is a portion of a line with 1 endpoint. Which means it moves forever in one direction. When we name a ray, we name it with the end point first. So, for example, if I wanted to talk about this set of points, I would call that ray AB. And if I wanted to talk about this set of points, I would have to call that ray BA, so that the endpoint is named first. And you see I've got those color coded there. We're going to spend most of our time discussing angles. Now an angle is 2 rays with a common endpoint. Two rays with a common endpoint. For example, and I apologize that these I'm not taking the time to draw nice straight lines. Let's make this A, B, C. Now I have some options about how I can choose to name this angle. I can name it by the vertex, angle B, but if I do that, sorry, that was not an angle symbol. If I do that, it doesn't necessarily tell me which of the 2 measures I'm interested in. For example, I could be talking about this in between, the smaller angle B, or I could be talking about this on the outside, the obtuse angle B. Now, that common endpoint is called a vertex. If I can choose to name the angle by its vertex, or I could name it ABC. We don't get into a lot of that. If I choose to name it using the points on the rays, I always put that vertex in the middle. The measure of an angle is generated by a rotation around the vertex from what we call the initial side to the terminal side. So if this is my initial side, and this is my terminal side of my angle, my rotation here might be counterclockwise. If it's counterclockwise, I have positive angle measure. So let's say that this is, 80 degrees. and that's, I didn't measure obviously, so it's probably not 80 degrees. But if this is still my initial side, still my terminal side, but I rotate clockwise, I'm looking at all of this. Well, one full turn is 360, and 360 minus 80 is going to be 280. It's a negative angle measure if that rotation direction is clockwise. Now these two bits of information are really important as we move through the semester. We have a positive angle measure if we're rotating counterclockwise, a negative angle measure if we're rotating clockwise. All right, let's look at our next page. And talk about degree measures of our angles. The degree measure is the most common unit to measure an angle. It's the one we're most familiar with. We just discussed the fact that one complete rotation around a vertex is 360 degrees. Therefore, 1 degree is 1/360th of a rotation. A lot of the time we look at right angles. "90 degrees is a right angle. "90 degrees is 90 out of 360, so that's 1/4 of a rotation. 180 degrees is 1/2 of a rotation. We would call that a straight angle. "180 degrees is a straight angle. Anything from 0 up to 90, less than 90 degrees, is acute. Anything greater than 90 degrees and less than 180 is obtuse. So if I'm in quadrant 1, if this were on my graph, quadrant 1 would be where the acute angles are. Quadrant 2 would be where I would find obtuse angles that measure between 90 and 180. Then our 180 degree rotation is our straight angle. Anything past that, from 180 to 360, that one full rotation, is what we call a reflex angle. And we're going to keep going in trig this semester. And anything larger than that, greater than 360 degrees, is what we refer to as angles of rotation. Angles of rotation. So we're usually really comfortable talking about acute and obtuse angles, right angles, straight angles. When we talk about reflex angles and these angles of rotation, that's when those are maybe some new terminologies for us. Okay, now we've already stated this, but let's go ahead and get it down again to make sure we don't forget. A counterclockwise rotation generates a positive angle measure, while a clockwise rotation gives us a negative angle measure. All right. Complementary and supplementary angles. An angle and its complement add to 90 degrees. An angle and its supplement add to 180 degrees. I can't talk today and write something different, sorry. So an angle and its complement add to 90, an angle and its supplement add to 180. The way I keep these straight is C comes before S in the alphabet, alphabetical order. C comes first, 90 is smaller. So 90 comes before 180, complement comes before supplement. Okay, so if I have an angle measuring 55 degrees, that angle and its complement together add to 90. So I can just do 90 minus 55. The measure of its complement is going to be 35 degrees. And the measure of its supplement is going to be the difference of that angle and 180. So in this case, it's going to be 125. I could also think about it, if this is the complement, then the supplement's going to be 90 degrees more because my difference is 90 degrees more from the original. So pause the video, see if you can figure out the complement and supplement of an 18-degree angle. Remember that the great thing about doing these guided notes online is that you have total control over the video. You can pause it, you can rewind, you can do what you need to do to make sure that you have time to understand and grasp the material and get it down in your notes. Okay, so a minute to reflect. For any angle, by how many degrees does the supplement differ from the complement? If I compare the supplement to the complement for both of these angles, I see that they are 90 degrees apart. Okay, let's look at that next page. Still talking about and focusing on complementary and supplementary angles. We're going to look at the measure of the angles marked. For A, I'm given a right angle, so the sum of these is 90 degrees. So 90 degrees is equal to 2x plus 3x. Those two angles together form my 90-degree angle. And I can solve that equation. I hope that you have your calculator handy. Remember, you are welcome to pause the video and work through these things. And then you can stop and check and see if you got it right. On B over here, I'm not starting with a right angle. Here I had that right angle, that 90-degree angle. Over here I have a straight angle. So my sum for this one is 180 instead of 90. There I go again. Whiteout is my friend today. 7x plus 2x. So that 180 degree straight angle is the same as 9x. And when I solve for x, I get a value of 20. X is 20 degrees. Now, degrees are not the only way to measure angles. We will also be talking about measuring angles in radians this semester. If you are in degrees, it is vital that you have that degree symbol. Otherwise, it does not mean what you think it means, and you can expect to be counted wrong. So make sure that you put those degree symbols when you are referencing degrees. Okay, degrees, minutes, and seconds. Our 360 degrees in a circle, we kind of tie them to measurements in exactness, like you would a clock with minutes and seconds. There are 60 minutes in 1 degree. So this link, there are 60 minutes in 1 degree, and there are 60 seconds in 1 minute. We use 1 apostrophe for minutes, 2 apostrophes for seconds. So 60 seconds in 1 minute, 60 minutes in 1 degree. That's my notation. If I am adding, we have to kind of think base 60. When we get 60 minutes, we have to carry over that degree. So when I'm adding minutes and degrees, it's easier to add those together if I stack them, so I can remember to carry when I need to carry. So right here, if I add these minutes, that is a total of 87 minutes. That is more than 1 degree. 60 minutes is 1 degree. So I'm going to have to take care of that here in a minute. 28 and 63 gives me 91 degrees. But like I just said, this is more than 1 degree. 87 minutes is 1 degree, 27 minutes, because 60 of those minutes make up 1 degree. So it's 1 degree, 27 minutes. and I need to combine that with my 91 degrees. So the final answer here is 92 degrees, 27 minutes. Stop and think and work your way through that if you need to again. And then we're going to talk about the subtraction problem. Again, make sure you take a second to stack things so that you don't forget what you're doing. Now, if I'm subtracting, I have to have something to subtract from. I can't just bring down that 29 minutes. I have to subtract it from something. So I'm going to have to borrow a minute, some minutes here, more than 1 minute. I'm going to borrow 1 degree, and 1 degree is equal to 60 minutes. So if I borrow 1 degree, this changes to 179 degrees. 1 degree is 60 minutes. So just like I would borrow 10 ones when if I were trying to subtract, I borrow 60 degrees. 60 minutes. Oh my goodness, 60 minutes. That's 1 degree. Okay, 60 minus 29 is 31 minutes. And then over here I have 179 minus 117. I don't need to regroup. I'm done. So take a second and look back through that. Make sure you understand how to do the subtraction. When we reflect down here, how many seconds are in 1 minute? Well, there are 60 seconds in 1 minute. So how many seconds are there in 1 degree? Well, there are 60 seconds in 1 minute. There are 60 minutes in 1 degree. So that is 60 seconds times 60. That means there are 3,600 seconds in 1 degree. There are 60 seconds in each minute. There are 60 minutes in each degree. So there are 3,600 seconds in 1 degree. All right, let's move to that next page. Let's talk about moving back and forth from decimal degrees to degrees, minutes, and seconds. Decimal degrees to degrees, minutes, and seconds. Now, I just realized I'm possibly going to need a calculator today, and I didn't grab mine, but that's okay. We're going to see what we can do without it. Now, when I am rounding, we're going to keep an extra digit. When you see that you're going to have to round, always keep an extra digit at least so that you can make sure you round correctly when you need to round. I'm going to convert 105 degrees, 20 minutes, 32 seconds to decimal degrees. So I'm going to rewrite this as fractions. I have 105 full degrees, so I know when I get my decimal degrees it's going to be 105 point something. Then I have 20 minutes out of the 60 minutes it takes to make 1 degree. And I have 32 seconds out of the 3,600 seconds it takes to make 1 degree. So these two fractions put together are going to give me my decimal. I'm told to round it to the nearest thousandth place, tenths, hundredths, thousandths. That's 3 decimal places I'm going to round to. Let me see if I have a calculator, guys. Alright, I do not apparently have a calculator home with me. That's okay though. Let's go ahead and let's finish what we got. If I plug this into my calculator and I add on, I should end up with about 105.342 degrees. 105.342, 342 thousandths of a degree. Alright. Now let's look at B. We're going to go back the other way. We're going to convert decimal degrees back into degrees, minutes, and seconds to the nearest second. So that gives me where I'm going to round, to the nearest second. Well, I know I have 85 full degrees, so we're going to start there. We've got 85 degrees. plus 0.263 tenths of a degree. If I am going backwards, to get it into decimals, I divided by 60. To get it back to seconds, I'm going to multiply by 60, or back into minutes, this one, by 60 minutes. So I take this decimal, 0.263, I multiply it times 60. It comes out to give me 15.78 minutes. So I've got 85 degrees, 15.78 minutes. So 85 degrees, 15 minutes. And now I need to take this decimal, this part of a minute, and turn it into seconds. Well, I've already multiplied by 60 once. So I'm not going to multiply by the full 3,600. Remember, we got this 3,600 by multiplying 60 times 60. I've already multiplied by 60 once. So I'm going to take this 0.78 and multiply it by 60 again to see how many seconds that is. When you plug this into your calculator, you get out 46.8 seconds, but I'm told to round to the nearest second. Well, 46.8 is about 47 seconds. So that's the seconds part of my answer, degrees, minutes, and seconds. If you've never used My Math Lab before, as you're doing the My Math Lab homework, there's going to be a show me an example option in the homework helps, and you can always have it show you again, and it will show you and talk you through it a little differently than exactly the way I'm doing it. Okay, standard position. When we are working with angles and trig, we typically are putting them on a XY coordinate plane. We know that an angle is in standard position if the vertex is at the origin and its initial side is at the positive x-axis. So this is my initial side. And once again, it's working you through to show you where the different types of angles fall. Quadrant 1 gives us our acute angles between 0 and 90, and then I have a quadrantal angle at 90 degrees. Quadrant 2 is my obtuse angles between 90 and 180, and then I have another quadrantal angle at 180 degrees. And then from 180 to 360, I have my reflex angles, except for 270, which is another quadrantal angle. My quadrantal angles are angles in standard position whose terminal side lies on the x or y axis. So those are my first three quadrantal angles. Well, 0 would really be first. Okay. Let's look at the next page. Coterminal angles. So because we are doing angles of rotation, that means we can rotate through and then come back around. And if we do that, we discover that angles are coterminal with each other. For example, 60 and 420 degrees. If I have an angle in standard position and its measure is 60 degrees, it's going to be right about here in quadrant 1. That's my 60-degree angle. But if I start at this initial side, the positive x-axis, and I rotate a full rotation, that's 360. And if I come back around another 60 degrees, that is a total of 420 degrees. So those two angles, 60 degrees and 420, have the same initial side. They started at the positive x-axis, and the same terminal side. It's just that one is acute and one is an angle of rotation. We say that angles like that are coterminal because they terminate at the same place. Their measures are always going to differ by a multiple of 360 degrees. Now I could just keep going. I could keep adding on 360 and coming back around. I would have an infinite number of angles that are coterminal with 60 degrees. All right, so let's take a look at some of these. We're going to do 3 examples really quick. Now, when I look at my 3 examples, the first thing I notice is that the first one is positive, the other 2 are negative. Remember that when I have a negative angle measure, that means my direction of rotation is clockwise. So let's look at this positive angle first, and let's see how many rotations I need to go through. Well, if you start thinking about multiples of 360, and you're probably going to need to grab your calculator for that. Multiples of 360, I've got 360 times 2 is 720. 360 times 3 is 1080, and that's nearly there, right? So if I subtract that 1080 degrees, I find that there's a difference of 26 degrees. So the angle of least positive measure that is coterminal with 1106 degrees is 26 degrees. That means that this 1106 degree angle is 1, 2, 3 full rotations and a little more. In fact, another 26 degrees more. 26 degrees is coterminal with 1106. Now notice I was moving in a counterclockwise rotation. Well, what about B? B is negative. Negative 150 degrees. Well, I know that this is 0, this is 180, so this would also be negative 180 if I rotated around this direction. If I'm just going 150, that means I'm going to go through quadrant 1 or quadrant 4, back into quadrant 3, and stop right here. This is going to be a negative 150 degrees right there. And my charge is to figure out what is the smallest coterminal positive angle. So if it's going to be positive, that means I rotate counterclockwise and stop at the same spot. Well, if I rotate counterclockwise, I go 180, and then I need to go another 30 degrees to reach this terminal side. 180 plus 30 is a positive 210. Another way to look at this mathematically would be to add that full rotation of 360 degrees here. A negative 150 and a positive 360 is a positive 210 degrees. That is where those 2 angles are coterminal. Alright, C, it's negative again, so I'm rotating clockwise more than 1 full rotation. I know that I'm going to go more than 1 rotation, so I'm going to go a full rotation, that's negative 360. Can I go 2 full rotations? 2 times 360 is 720. So if I add 720 here, a negative 603 and a positive 720 is a 117 degree angle. Well, if this is 90, 117 is going to be, about right there. So I would, to get my negative 603, I would go a full negative 360, and I would keep going until I hit that spot. So negative 603 is coterminal with 117 degrees. They terminate or end at the same location. Alright, another way we talk about angles of rotation, anytime we are turning, one wonderful thing about Trig is that we have a lot of direct applications. Angles of rotation, axles turn, pulleys turn, gears turn. So anything that has that rotation motion is going to be a direct application for trigonometry. If we analyze the revolutions of a wheel makes 270 revolutions per minute. Through how many degrees will a point on the edge of the wheel move in 5 seconds? We're going to need to look at some conversion factors here. We're going to talk about some dimensional analysis, but first let's talk about what we know. We know that this wheel does 270 revolutions in 1 minute of time. And I know that 1 minute is the same thing as 60 seconds. Now we're talking time, not degree, portions of a degree. 270 revolutions in 1 minute is 270 revolutions in 60 seconds, right? Because 1 minute is 60 seconds. What I want to know is how many revolutions that would be, first of all, in 5 seconds. So I can set this up as a proportion, and I can say, okay, I can solve a proportion with cross products. So if I multiply 270 times 5, that's going to be equal to 60x. 60x equals 270 times 5. So 270 times 5 divided by 60, I figure that that will go through 22.5 revolutions. That's my missing value. 22.5 revolutions in 5 seconds, which makes sense because if they can do 270 revolutions in a minute in 60 seconds, yeah, 22 and a half in 5, that works. But our answer doesn't need to be in revolutions. Our answer needs to be in degrees. Well, a revolution is 1 turn all the way around, which is 360 degrees. That means that that wheel can turn through 8,100 degrees in those 5 seconds. Now that's one way to work through and reason through that problem. Another way is through what we call dimensional analysis. If you have done a physics class or some of your science classes, you've done dimensional analysis. It's a much more organized way to approach this. We will be doing some dimensional analysis a little bit further on in the semester in addition to this type of problem. So we have our starting place. We have 270 revolutions per minute, and we are going to cancel out units to get to the units we want using conversion factors. Conversion factors tell me that two things are equal. For example, I know there are 12 inches in 1 foot. I can write that as 12 inches over 1 foot, or I can write it as 1 foot over 12 inches. Those are conversion factors, and I'm going to stack them the way I want to stack them to move from one thing to the next. Now, I need to go from minutes to seconds because I need 5 seconds, right? So I'm going to say, okay, I need to move away from minutes into seconds. I want my minutes to cancel. And I know that 1 minute is the same thing as 60 seconds. So now my minutes have canceled out and I'm in seconds. That's good. That's what I needed to be in. So I've got revolutions and I've got seconds. I need degrees instead of revolutions. So 270 revolutions. I've got revolutions in the numerator that needs to divide out. So revolutions over revolutions. And 1 revolution, 1 full turn, is 360 degrees. So that's going to divide out those units of revolutions, and now I'm in degrees per second. Now this problem has one final step. I want to know how many degrees the wheel will turn through, revolve through in 5 seconds. So I'm going to take that and I'm going to multiply it times 5 seconds. And I'm just going to put that over 1 because stacking them all up makes me happy. The seconds cancel out because I have seconds in the numerator and denominator, and I'm left in terms of degrees, which gives me my 8,100 degrees. All right, let's do another dimensional analysis problem just to kind of get a little bit of practice. I really want you to pause the video, read the problem, see if you can make a little bit of progress setting it up, and then start me back up and we will work through it together. So we have a CD player. It makes 480 revolutions per minute. Same situation. We want to know how many degrees a point on the CD will move in 2 seconds. So we've got 480 revolutions per minute. We need to turn that into seconds. So my minutes are going to cancel. 1 minute is 60 seconds. I need to move from revolutions to degrees. So revolutions needs to cancel. 1 revolution is 360 degrees. And I'm interested in a length of time of 2 seconds. So that's going to be times 2 seconds just over 1. That cancels out seconds, and I'm left in terms of degrees. Multiply through my numerator, multiply through my denominator, and then divide that out. The point on my CD will rotate 5,760 degrees in 2 seconds. That's really fast. Okay, one type of homework problem that you're going to see in my math lab is clock math. And I wanted to do an example here to kind of give you a heads up and a start on this. We're going to find the measure of the smaller angle formed by the clock hands at 2:05. Well, at 2:05, my minute hand, my long hand, is pointing at the 1. And my short hand, my hour hand, if at 2 o'clock it was at 2, but it's moved a little past 2 because it's now 2:05, right? So my hour hand is going to be a little bit past the 2. So if I'm wanting to find the measure of the smaller angle formed by the clock hands, I want this measure right here, this angle. And we're going to call this angle theta. Theta is just a Greek symbol representing any angle. You're going to see us use that a lot. That's my missing angle that I'm looking for. Well, let's reason through this a little bit. My clock is divided up into equal increments all the way around, 12 equal increments all the way around. So if I take a full rotation, that 360 degrees is divided into 12 equal increments from one number to the next. That gives me 30 degrees per time increment. So when the clock, for example, over here, when I have this sector from the hand moves from 10 to 11, that is 30 degrees. From 11 to 12 is 30 degrees. So I know that from 1 to 2 is 30 degrees, but I've gone a little bit past the 2. So I've got to figure out what is that little piece that I have gone past 2 o'clock. Well, I've gone 5 minutes because it's at 2:05. I've gone 5 minutes out of the hour. So I've gone 5/60ths of an hour past 2 o'clock. And 5/60ths reduces to 1/12 of an hour. So I've moved 1/12 of an hour. My hour hand has moved 1/12 of the way from 2 to 3 o'clock. Well, this angle from 2 to 3 o'clock, another 30-degree angle. So I've moved 1/12 of that 30-degree angle. So 1/12 of 30 degrees comes out to be 2.5 degrees. So this is 30 degrees from 1 to 2, and this is 2.5 degrees, which means my value for theta, the opening between the two hands at 2:05, is 32.5 degrees. Now you're going to see this clock problem set up a little bit differently in different places, but the basics are going to be the same. The central angle between any two numbers is going to be a 30-degree angle because of the way our clock face is built.